Have you ever just looked up at a jumbo jet cruising at 30,000 feet and really thought about it? How does that thing, that massive piece of metal, actually stay up there? We all kind of think we know the answer, but what if the story we were taught in school isn't the whole story?
I mean, seriously, let that sink in. We're talking about almost 1 million pounds of plane, people, and luggage just effortlessly hanging out in the sky. It seems to defy the laws of physics. But of course, there's a popular explanation for how it all works.
And it all centers on this guy right here, the classic teardrop-shaped wing, or airfoil. You know the one. It's flat on the bottom and has that beautiful curve on the top. This shape is the hero of the story most of us learned.
Right, so the theory goes something like this. As the wing slices through the air splits at the front. Now, because the top is curved, it's a longer journey. So the air molecules going over the top have to speed up to meet their buddies from the bottom at the exact same time at the back of the wing. And thanks to Bernoulli's principle, faster moving air means lower pressure. So you get high pressure on the bottom pushing up, low pressure on the top pulling up, and poof, you've got lift.
It's a really neat idea. It's so intuitive, it's easy to picture, and, well, it's just not right. Or at least, it's not nearly the whole picture. So let's start poking some holes in this thing.
The second you start actually looking at how planes fly in the real world, that nice, clean story starts to get, well, messy.
And here is Exhibit A. It's the first giant crack in the theory. If that special curved top is absolutely required for lift, then what in the world happens when a pilot does this? Think about it. When the plane is upside down, that longer path is now on the bottom. According to the equal transit theory, that should be creating a force that literally sucks the plane down towards the ground. But clearly, that's not what's happening. These pilots are doing just fine. Something else is going on.
And it doesn't stop there. Lots of aerobatic planes have wings that are perfectly symmetrical. The top and bottom are identical. How does the theory explain that? And what about a paper airplane? It flies with a wing that's just a flat piece of paper. And let's not forget the Wright brothers. Their first wings were super thin and barely had any curve at all. None of these examples fit that classic model.
And here's the real kicker. The central idea of the theory, that the air particles have to meet up at the back of the wing at the same time, is just made up. There's no law of physics that requires it. In fact, when you test it in a wind tunnel, the air going over the top actually gets to the back of the wing way faster than the air underneath. The equal transit part of the theory is just plain wrong.
Okay, so if the story we all learned is wrong, then what's the real answer? Well, it turns out the truth is actually simpler and, frankly, a lot more powerful.
Let's forget about airflow for just a second and go all the way back to high school physics, to good old Sir Isaac Newton. You know this one. For every action, there is an equal and opposite reaction.
The key idea is this. If you want to make a really heavy thing go up, you have to push something else down. It's that simple. A rocket works by pushing hot gas down at incredible speed. A helicopter's blades push a giant column of air down. The upward motion, the lift, is just the reaction to that downward action.
So, that's the whole secret. An airplane flies by pushing air down. That's it. A wing is just a really, really clever and efficient shape for grabbing a huge amount of air and throwing it downwards. Newton's third law handles the rest.
Okay, so the next logical question is, how does a wing do that, especially a flat one or a symmetrical one? Well, it all comes down to the angle. We need to talk about one of the most important ideas in flying, the angle of attack. And critically, this is not the angle of the wing to the ground. It's the angle between the wing and the air that's rushing towards it. You know this instinctively. Put your hand out the window of a moving car. If it's flat, the air flows right over. But if you tilt the front edge up just a little, you feel your hand get pushed out. That tilt is your angle of attack.
And it's a pretty straightforward relationship. A small angle of attack pushes a little air down, giving you a little lift. Want more lift to climb? A pilot just pulls back on the stick, increasing that angle, which pushes more air down, creating more lift. But you can't do that forever. There is a limit.
And suddenly, all our earlier mysteries are solved. How does a flat paper airplane fly? Because its wing is angled to the oncoming air, pushing it down. How does a stunt plane fly upside down? The pilot just points the nose of the plane up, which gives the inverted wings a positive angle of attack. It's all about the angle.
So what happens if you increase that angle of attack too much? Well, the air can't make that sharp turn over the wing anymore. The flow separates from the surface, becoming turbulent chaos. This is called an aerodynamic stall, and it's super dangerous because the wing suddenly stops pushing air down effectively and you lose lift.
All right, so you might be thinking, okay, if it's all about the angle, then why do we even bother with that fancy curved teardrop shape? Why aren't all wings just flat planks? And that is an excellent question.
Here's how you can think about the two working together. The angle of attack is the primary cause of lift. It's what makes the magic happen. The wing's special shape, the airfoil, is what optimizes that magic. It helps the airflow stay smooth and attached to the wing over a much wider range of angles, which makes the whole process way more efficient and delays a dangerous stall.
So to put it simply, a flat board can fly, but it's not very good at it. That brilliant curved aerofoil shape is an engineering marvel designed to generate lift as efficiently and as safely as possible. The shape doesn't create the lift, it makes the lift better. It's an optimizer, not the originator.
So, let's bring it all home. After busting the myths and digging into the real physics, what's the one thing you really need to remember about how planes fly?
Think about everything from that flimsy paper airplane you made as a kid to the most advanced supersonic jet. What is the one single universal thing that they all have to do to stay in the air?
That's it. It's that simple. They fly because they are constantly grabbing a huge volume of air and forcing it downwards. And because of good old Newton, the atmosphere pushes right back up.